Hello everyone, I'm truly honored to take part in this conference celebrating the 100th analog space mission organized by the Analog Astronaut Training Center. My name is Mateusz Koba and I'm a recent graduate in biomedical engineering with a specialization in medical electronics and informatics from AGH University of Science and Technology in Krakow. In my daily work, I develop, integrate, and program advanced custom-made measurement systems and devices. The topic of my presentation today is construction of a non-invasive sensor for measuring vitamin D concentration with application of predictive modeling in isolation conditions during simulations of space missions. This was also the subject of my engineering thesis at AGH, which I successfully defended almost 2 years ago. I'd like to take you through what we managed to discover and achieve during this project. Let's start with a short introduction about vitamin D and its role in the human body. I call it a life-sustaining molecule, and not without reason. Vitamin D affects almost every system in our body, so maintaining its proper level is crucial. Both deficiency and excess can lead to serious, sometimes irreversible problems. For example, too little vitamin D weakens the bones, speeds up osteoporosis, and causes chronic pain. Too much can lead to hypercalcemia and kidney damage. Because vitamin D is fat soluble, it can be overdosed, especially in people with low body fat. Without an optimal level, the body loses balance, which may trigger many disorders and diseases. So, why did I decide to focus on vitamin D in the first place? The idea came during my participation in 48th Analog Space Mission organized by AATC, called Sustainable Earth, Sustainable Universe. At that time, I was working on a completely different project, studying physiological changes in human eyes caused by isolation from ultraviolet light. Although we collected a lot of data, the equipment available didn't allow us to observe significant effects. However, while analyzing the results, I started thinking about how the lack of sunlight might influence other body functions, especially vitamin D production, which depends directly on skin exposure to UVB light. When I began reading scientific papers on vitamin D deficiency, I realized that there is still no non-invasive way to measure this vitamin. Every quantitative test today requires collecting body fluids, usually blood or plasma, and analyzing them in a laboratory with expensive equipment. For astronauts, this becomes an even bigger problem. Because they must cover their bodies to protect themselves from cosmic radiation, their skin can't synthesize vitamin D naturally, so they have to take supplements. But how much should they take? That's not easy to determine. Everyone's body reacts differently to supplementation. Carrying heavy lab equipment into space and performing invasive blood tests are both impractical. That's why I came up with an idea to creating a portable, lightweight, non-invasive device that could measure vitamin D levels in real time using bioimpedance analysis. So let me briefly explain what bioimpedance measurement actually means. In this method, a small alternating current of a given frequency and constant amplitude is applied to the skin through two electrodes. Different frequencies interact with different substances in the tissue. This current creates a voltage between the electrodes, which is slightly out of phase because the skin has capacitive properties. By measuring the phase shift between the current and the voltage, we can determine the concentration of certain substances, provided we know the relationship between the phase angle and the substance concentration. So, how does this relate to vitamin D? Previous studies have shown a correlation between phase angle and the vitamin D concentration at around 21 Hz. The method is safe because it uses a very low alternating current. However, the relationship has not been studied for other frequencies, and the overall knowledge in this area remains very limited. My goal, therefore, was to expand our understanding of bioimpedance based vitamin D measurements and to design a non invasive sensor capable of doing it. The experiment consisted of five main stages: designing, simulating, and building the prototype, developing communication and control method for the device, testing and validating the prototype on an artificial skin model, creating a predictive model to estimate vitamin D concentration, conducting measurements on volunteers, and estimating their vitamin D levels using the model. For the prototype, I used an external sound card. It was easy to control and could generate a clean sine wave between 20 and 24 Hz, which is within the audible range. The signal was conditioned using a preamplifier with a low-pass filter, which increased amplitude and reduced noise. A voltage-controlled current source maintained a constant current of 80 microamps. Then using a buffer amplifier and current shunt, the current waveform was measured and compared to the output voltage. Finally, the signals were filtered to remove interference from power lines, muscle activity, and heartbeat before the phase difference was calculated. Here you can see the prototype, built with standard electronic components and breadboards. For the actual test, I used biomedical gel electrodes, the same kind used in ECG measurements. For communication, I wrote two simple MicroPython scripts. One ran on the Raspberry Pi Pico W, which acts as a client sending measurement data over Wi-Fi. The other script running on a PC server received and processed this data. The graphical user interface was built in LabVIEW, along with the control logic and server communication. Through this panel, user could select a specific frequency or choose a multiple frequencies option, which perform measurements from 20 to 24 Hz in 0.2 Hz steps, lasting 3 seconds each. After each test, the system displayed the phase shift, impedance magnitude, and estimated vitamin D concentration. Before testing on human skin, I performed measurements on a simulated skin sample made of bacterial cellulose grown at AATC. I connected electrodes to the sample and tested different vitamin D concentrations. The vitamin D came from open supplement capsules, each containing 100 micrograms, and was spread over the cellulose surface. The results showed that the electrical response, specifically the phase shift, was similar for both the cellulose model and human skin at certain frequencies. That's why the predictive model was developed using the cellulose samples. As the vitamin D concentration increased on the cellulose surface, a clear correlation was observed between concentration and phase shift. A linear fit method was used to calculate the R-squared correlation coefficient, and frequencies with the highest R-squared values were selected for further analysis. The table here shows the regression equation of those predictive models. As you can see, the highest R-squared value was obtained at 24 Hz. After developing the model, measurements were performed on human skin. The electrodes were placed on the forearm. Two current electrodes and two voltage electrodes, each spaced 2 cm apart. The study included 2 volunteers, and the results are shown here. The measured values varied between different frequencies, but were consistent between both participants when using the same frequency. To summarize, the results differed across frequencies but remained similar for both individuals at the same frequency. A significant difference between the two participants appeared only at 22 Hz. For 20.2 Hz and 22 Hz, the measured vitamin D levels corresponded to typical human concentration, which suggested these readings were likely accurate. The unusually high results at other frequencies were probably caused by interference from other substances in the blood that also affect the bioimpedance phase angle. After completing my engineering thesis, I decided to continue this research as a part of my master's project, since the topic was still far from being fully explored. With the great support of Agata Kołodziejczyk, who supervised both my engineering and master's project and is also the director of AATC, I was able to further develop the system. The device you see on this slide is its improved version. It no longer looks like a prototype, but rather like a near-finished product. There's still a lot of work ahead to validate the bioimpedance method, but if it proves successful, it could help astronauts maintain their health during space missions, and also benefit ordinary people who lack regular access to medical care but suffer from vitamin D deficiency without realizing it. Introducing such a device could truly revolutionize medicine, making safe, affordable, and non-invasive biomedical measurements available to everyone. And that's all I wanted to share with you today. Thank you very much for your attention.